Welcome to Module 1 of our course, Linear Algebra and Differential Equations. This first module will focus on linear algebra, the branch of mathematics that deals with vector spaces, linear transformations, matrices, determinants, and systems of linear equations. Linear algebra is not only the language of modern science and engineering, it's the toolbox you'll use to handle large systems of equations, analyze networks, model real-world problems, and work with data. Whether you're an engineer designing a control system, a physicist modeling particle interactions, or a computer scientist creating algorithms, linear algebra will be part of your daily work. Our journey in this module will move through vectors and vector spaces, matrices and determinants, cofactor expansion and matrix inverses, rank and linear independence, solutions of linear systems, positive definite matrices, linear transformations, operations on matrices, inner products, orthogonality, and the least squares method. By the time we finish, you'll see how these topics connect, and you'll be able to handle problems that at first might seem impossible without these tools. 1. Vectors and vector spaces. A vector is more than just a quantity with direction and magnitude, it's a fundamental object in mathematics and physics. In the physical world, you might think of velocity as a vector, having both speed and direction. In mathematics, vectors can also represent abstract data points, such as a set of numbers describing a chemical mixture or an economic model. 1.1 Representations of vectors. We can represent vectors in many ways, as arrows in space, as columns of numbers, or as abstract elements of a vector space. For example, in three-dimensional space, you might describe a vector by three numbers, one for each coordinate direction. 1.2 Vector spaces. A vector space is a collection of vectors that can be added together and multiplied by numbers, called scalars, while staying in the same collection. For example, the set of all two-dimensional vectors forms a vector space. The set of all three-dimensional vectors forms another vector space. Even the set of all continuous functions can form a vector space under addition and scalar multiplication. Vector spaces are defined by a set of rules, such as closure under addition and scalar multiplication, the existence of a zero vector, and the presence of additive inverses. 2. Matrices and determinants. 2.1 Matrices. A matrix is a rectangular array of numbers arranged in rows and columns. You can think of it as a compact way to store coefficients for a system of equations, or as a transformation that moves vectors from one place to another. 2.2 Determinants. The determinant is a single number associated with a square matrix that tells you important information about the matrix. If the determinant is 0, the matrix is said to be singular, meaning it does not have an inverse and cannot uniquely solve certain systems of equations. If the determinant is non-zero, the matrix is invertible, and the system of equations it represents has a unique solution. The determinant also tells us about the scaling factor of the transformation represented by a matrix, for example, how much a transformation stretches or compresses area or volume. 3. Cofactor expansion and matrix inverses. 3.1 Cofactor expansion. Cofactor expansion is a method for calculating the determinant of a matrix by breaking it down into smaller pieces. You choose a row or a column, multiply each entry by its cofactor, and sum the results. This approach is especially useful for small matrices, but it's also conceptually important because it reveals the recursive structure of determinants. 3.2 Inverse of a matrix. The inverse of a square matrix is another matrix that, when multiplied by the original, gives the identity matrix. In practical terms, finding the inverse is the matrix equivalent of dividing by a number. However, not all matrices have inverses, only those that are non-singular, the determinant not equal to 0, do. One method of finding an inverse is to compute the matrix of cofactors, take its transpose, called the aggregate, and then divide by the determinant. 4. Rank and linear independence. 4.1 Rank of a matrix. The rank of a matrix is the maximum number of linearly independent rows or columns. It tells us about the dimension of the space spanned by the rows or columns of the matrix. Rank is critical in solving systems of equations. It can tell you whether a system has a unique solution, infinitely many solutions, or no solution at all. 4.2 Linear independence. A set of vectors is linearly independent if no vector in the set can be expressed as a combination of the others. If at least one vector can be formed from the others, the set is linearly dependent. In solving problems, checking for linear independence is essential when deciding if your set of vectors is enough to describe the space you're working in. 5. Solutions of linear systems. A linear system is a set of equations where each equation is linear in the variables. For example, you might have 3 equations in 3 unknowns, each involving only first powers of the variables. We can solve linear systems in several ways. Substitution, solving one equation for a variable and substituting into others. Elimination, adding or subtracting equations to remove variables step by step. Matrix methods, using Gaussian elimination or matrix inverses. The relationship between the number of equations, the number of unknowns, and the rank of the coefficient matrix determines whether there's a unique solution, infinitely many, or none at all. 6. Positive definite matrices. A positive definite matrix is a special kind of symmetric matrix that has certain desirable properties. In geometric terms, it defines shapes like ellipses and paraboloids, and in optimization, it guarantees that a function has a unique minimum. These matrices appear in engineering when analyzing stability, energy, and optimization problems. One key feature, for any non-zero vector, the associated quadratic form is always positive. 7. Linear transformations. A linear transformation is a function between vector spaces that preserves vector addition and scalar multiplication. For example, rotating a vector in space, reflecting it across a plane, or scaling it up or down, all can be described as linear transformations if they preserve the straightness of lines and the origin. In practical work, linear transformations are often represented by matrices, making it possible to use matrix operations to study their effects. 8. Operations on matrices, linear products, orthogonality, and least squares. 8.1 Operations on matrices. Matrix operations include addition, subtraction, scalar multiplication, and matrix multiplication. Multiplication is not commutative, meaning the order matters, but it is associative and distributive over addition. 8.2 Inner product and orthogonality. The inner product, or dot product, between two vectors gives a measure of how aligned they are. If the inner product is 0, the vectors are orthogonal, meaning they meet at a right angle. Orthogonality plays a major role in simplifying problems, such as when working with orthogonal bases in vector spaces. 8.3 The least squares method. When a system of equations doesn't have an exact solution, perhaps because it's overdetermined, we can use the least squares method to find an approximate solution that minimizes the error. This is especially common in data fitting, where you want the best fit line through a cloud of points. Module 1 Summary. In this first module, we have built a foundation in linear algebra, from the basic building blocks of vectors and vector spaces, through matrices, determinants, and their properties, to advanced concepts like orthogonality and least squares. These tools are not isolated facts, they form a connected framework you will use repeatedly in mathematics, engineering, and the sciences.